Here's one for you to try. See if you can use the limit definition of the derivative to find the equation of the line tangent to f of x equals 1 over x at the point a equals -5. And when you do this, put your final answer in slope-intercept form, because that's how we usually represent lines in the final answer, but you probably want to start with point-slope form. So pause the video, see if you can find that equation of the tangent line. Okay, so let's take a look at this together. We begin with the point-slope version of a line, y minus y1 equals mx minus x1, and we already have x1, which is -5, so we need our y1, but y1 is simply f of -5, so that's -1/5. Okay, so there's x1, y1, and now we need the slope. Well, the slope is just simply f prime of -5, right? So to find f prime at -5, we first need to find f prime of x in general, and then once we have that, we'll evaluate it specifically at -5. Recall that the limit definition of the derivative is limit as h goes to 0 of f of x plus h minus f of x all over h. In our particular case of f of x equals 1 over x, we have the limit as h goes to 0 of 1 over x plus h minus 1 over x all over h. That first term there is f of x plus h, and the second term is f of x. Next, we need to do something with these denominators, x plus h and x. So let's do an LCD, least common denominator of, well, it looks like it's going to be x times x plus h. Okay, so that means we need to multiply the first term by x over x, and the second term by x plus h over x plus h to get that denominator sorted out. This gives us the limit as h goes to 0 of, let's see, x minus the quantity x plus h all over h x plus h. Remember, when you have a fraction all over a number, that fraction bumps down a level, a over b, c, which is why I bumped this down to include this h down here. This was just a big fraction up in the numerator, so I bumped it down a level to include that h. Well, now we're in business because we start to get some cancellation. We have the limit as h goes to 0. Look what happens. These x terms cancel, and we're left with -h up top over h times the quantity x plus h down below. And finally, our h's cancel. That's what we wanted to do. We needed to get rid of that h in the denominator. So now we simply have the limit as h goes to 0 of -1 over x plus h. And we can simply evaluate that limit by plugging in 0. So -1 over x squared. That's plugging in 0 for h, that is. Oop. Okay, so we now have the derivative of the function at any point x. That's good news. We are particularly interested in evaluating this derivative at x equals -5. So we can say f prime of -5. Plugging that in, we have -1 over -5 squared, which is -1 over 25, and that's our slope. So finally, we can plug this into our point-slope form of the line. Switch to blue for this part of it, so we have y minus a -1/5, so that makes it y plus 1/5 equals the slope, -1 over 25, x minus a -5, so x plus 5. And then let's just clean this up so it's in slope-intercept form. Let's see. I'm gonna subtract this 1/5 from both sides after I distribute this -1 over 25 through. So -1 over 25x minus 1/5, and then minus another 1/5. This gives us a final answer, it looks like, of y equals -1/25 x minus 2/5. There we go. That is the equation of our tangent line at the point a equals -5. Just to get an idea of what this looks like graphically, I've plotted the curve 1 over x along with that tangent line, negative 1/25 x minus 2/5. And you can see right at that point x equals -5, that tangent line comes up and just touches the original function. It gives us a line that touches the curve just at that one point, so it's good to have a visual understanding of what all these calculations are actually telling us.